Namaste. Welcome to this channel, Dr.ARM's Chemistry. Friends, we were discussing charge transfer spectra for transition metal complexes. And last time we have seen the ligand to metal charge transfer spectra in some cases as examples. Today we will see the charge transfer spectra in case of the metal ligand transitions. So the second type is metal ligand transition. So this is metal ligand transition. So such transitions are taking place in complexes where the metal ion has high energy filled d orbitals, whereas ligands are empty by star symmetry, low energy orbitals. So the d orbitals of metal ion which are lying at higher energy level. So if we see this axis, and these are the metal energy orbitals which are filled. These are filled, and the transition metals, so these empty orbitals are relatively low lying. So they are relatively low lying pi star orbitals of ligands. So metal transitions are taking place from these. So these filled electrons are moving to these empty ligands. So best example for such type of complexes can be explained using some ligands. So we can take the example of ligands such as, so the ligands can be carbon monoxide, cyan, cyano ligands, or aromatic amines, that is aryl amines. For example, we can have the pyridine, similarly bipyridine or phenanthrone. So these ligands can be used for this purpose in the complex. Means if such ligands are there, then the complex will show this metal ligand type of transition. So we will discuss some examples of such type of transitions. For example, if we see the complex that is CrCO6, or we can have molybdenum complex MO. We can have MoCO6, that is hexacarbonyl molybdenum, hexacarbonyl chromium. So in such case of complexes, if we observe the spectra of such complexes, then we find that these complexes gives intense colored, intense bands, strong bands, which are appearing at higher energy levels. So for example, in case of chromium complexes, The absorption bands are observed at 35,800 per centimeter frequency. This is first band. Second band is appearing at 44,500 per centimeter. Similarly, in case of this molybdenum, we can have the first band at 35,000 per centimeter, and second band is observed at 43,000 per centimeter. So in this way we can have all the observed bands can be assigned here. Now here you will observe that the absorption spectrum shows the intense band like this. So these bands are intense, means broad bands, which are also elevated, and these bands may include the transitions, DD transitions to some extent are. They are also include some smaller bands, but their significance is very low. Therefore, these bands are major bands. Now we will take second example. Another example we will see here. In case of this nickel NiCO4 tetracarbonyl nickel. This also gives the metal to ligand bonds. Now here these bands are not as strong as these bands. The bands which are appearing here, absorption bands, these are not as strong as these bands. So these are having medium to strong range. So these are appearing at relatively a lower energy level. So for example, 32,000 per centimeter. Then second band appears at 35,200 per centimeter. Third band appears at 37,600 per centimeter. So these three bands are assigned to tetracarbonyl nickel complex. So here the three types of filled orbitals are involved here. Three types of filled orbitals of metal nickel are involved here. So nickel we have these orbitals, that is dxy, dz2, dzx and dyz. So these are lowest energy orbitals which are formed from, these are lowest energy orbitals formed from pi star orbitals. Pi star orbitals of the set of CN group of Ligand group orbitals of CN. Ligand group orbitals is set of the 4 CN minus 4 CO. CN minus, we are taking here CN minus. Only CN. These are neutral species. The 4 CN groups are involved here, which are giving rise to these orbitals of metal ions, which are containing electrons, and these electrons are transferred to the vacant orbitals, p orbitals of carbon. So this is d pi to p pi transition, d pi to p pi. This will be this nickel has d pi to p pi transitions. So this is about these metal to ligand transitions. Now we will see some of the important features of these transitions, metal to ligand and ligand to metal charge transfer transitions. We will see the few examples as a characteristic of such charge transfer transitions. We know that the complexes such as HgI4, HgI2, and another complex is MnO4 minus. So these complexes are having intense color. This intense color indicates that the charge transfer takes place in visible region of the spectrum, visible region of the spectrum, and that is when the color is intense. Here the charge transfer transitions are taking place here in this way, that is p pi to d pi or d pi to p pi. But here only the charge transfer occurs into the visible region, as we have seen earlier. It will affect the color of the compound or complex. So here this HgI2 shows that it has D10 configuration. The d electrons are full and it shows the brick red color, whereas this Mn has D0 configuration with intense purple color. So in this way, the two substances can be distinguished from each other. The bright colors of these complexes result from ligand to metal. So they are showing, here we will show ligand to metal. So p pi of ligand shows transfer of electrons or charge to d pi of metals, or the d pi of metals to p pi of ligands. The ligand to metal, so these are ligands. So this d pi is also of ligands. Now another example, heroin indicator. Heroin indicator. So this heroin indicator has the species of iron, tris phenanthroline iron, tris phenanthroline iron in 2+ and 3+, that is mixed oxide, that is it has the mixed oxide form. So this is our phenanthroline. If this phenanthroline is in the 2+ state, during charge transfer. So here the Fe is in the, we will show first this reaction. It is converted into 3 plus T with loss of or transfer of 1 electron. Now here this Fe is in the 2 plus T and this Fe is in the 3 plus state. So this configuration of this Fe is D6 and this is low spin, whereas this Fe is in D5 configuration and it is high spin. Now colors exhibited by these complexes. This species shows blood red color, whereas this species gives pale blue color, Now we will see that the reaction is taking place in reversible way. Means this ion which is containing Fe2 plus state is converted into the Fe complex in 3 plus state. Means the Fe, the complex already contains, we have seen that the complex solution contains both ions Fe2 plus as well as Fe3 plus. So this Fe acts as, in other words we can say this Fe2 plus loses its electron and this Fe is converted into Fe3 plus. Means this is oxidized. If the reaction is taking place in this direction, what happens? The electron is added to this Fe3 plus and it is converted into Fe2 plus. So in that case, this complex shows the reduction. So it is Fe3 plus is reduced to Fe2 plus. Or in this way, this Fe2 plus is oxidized to Fe3 plus with the loss of 1 electron. So in this way, the ferrine complex is showing different colors under different conditions. So the visible spectra of this trisphenanthroline iron 2 plus is similar to cobalt 3 complex also. So this is also because of metal to ligand charge transfer. Now this phenanthroline, has a structure like this. So you must know the structure. This is phenanthroline. So the possibility of this oxidation of Fe2 plus is shown here. So this is because of the metal to ligand charge transfer. Here as a result of Fe2 plus complex of unsaturated amines. So this is unsaturated amine, that is phenanthroline. The colors exhibited are intense. The charge transfer bands of this complex are appearing because they have very high molar absorptivities. So these complexes, because of this unsaturated ligand, have high molar absorptivities. This is larger than the degree transition which is taking place in case of these Fe metals. So DT transition is different than charge transfer transitions. DT transition requires very small amount of energy, whereas the charge transfer transition requires very high amount of energy. So DT transitions are appearing towards right side in the spectrum, whereas the charge transfer transitions are taking place towards the left side of the spectrum or towards near UV, that is UV region. So the Fe3 oxidation state and the strong or strength of the ligand also plays important role in the charge transfer transitions. Since Fe3 plus is a strong oxidizing agent, the electron acceptor, Fe3 plus is electron acceptor. So here this is oxidizing agent, means this is donor, and this is electron acceptor. So this Fe accepts this electron and gives back this Fe. Then the unsaturated phenanthroline is more suitable for metal to ligand charge transfer than ligand to metal. So this is this gives the charge transfer transitions. The charge transfer transitions exhibited in such cases are less powerful or less intense than the DD transitions. Therefore, charge transfer transitions are not observed here, but the DD transitions are more expected. The color change of this ferrone indicator is due to the difference in the intensities of DD transition and the charge transfer band. The charge transfer, this charge transfer is also affected by the exchange of ligand or the ion or the solvent. Means if we change the solvent or if we change the ion, then it affects the magnitude of the charge transfer transition. The symmetry also affects the transitions. So three important, means another important factor about this charge transfer transition. We have seen the ligand to metal charge transfer transition, metal to ligand charge transfer transitions, and the third is intra ligand charge transfer. Intra-ligand charge transfer. So for example, if we take the ligand like this, SCN minus. So this ligand has two centers which shows or which are involved in the charge transfer. So there are many such ligands which are having two centers. Here the electron or charge is moving from one atom of that ligand to the another atom. So this charge may be delocalized over S sulfur terminal, and this type of transition is called intra-ligand transitions. So it shows no involvement of metal. So metal shows no interference in this type of intra-ligand charge transfer. Metal remains isolated. Then we will see metal to ligand charge transfer. For this purpose, we can see the energy level diagram also. So if we show this is energy axis, and if we show the metal orbitals, and here the ligand group orbitals, and in between here if we see the Ml6 octet complex orbitals, MOs. So here the d orbitals, we know that there are 5 d orbitals which are represented 1, 3, 4, 5 like this. Then there is s orbital. This is 4s or A1G symmetry orbital. Then there are 3 T2G symmetry orbitals. Then on this side we will have the 6 ligand group orbitals, Ml6. So these are ligand. So these are sigma. Now there is a pi orbital. There is a pi orbital. This is a sigma pi orbital, and another there is the pi star orbital of ligand groups. Now we will have the molecular orbitals of these metal atoms. So we will have this ligand group orbital of sigma symmetry and metal group orbital, that is 4s A1G symmetry. So this will contain the EG symmetry orbitals plus T2G symmetry orbitals, and this is P1U symmetry orbitals, that is P orbitals, 4 P orbitals. Now on this side, the ligand group orbitals of sigma symmetry are also bonded here. So this is called A1G symmetry orbital. Then there are 2 orbitals of EG symmetry, and there are also EG symmetry orbitals in this, like this. Then this 4p will produce T1U symmetry orbitals from this EG. Now there are, so this T2G will have no matching symmetry orbitals. So these 3 orbitals will remain non-bonding. We will label it later on. Then there are EG symmetry orbitals, EG star, 2 orbitals. So they will have matching symmetry orbitals. From this EG symmetry, then A1G symmetry orbitals. Like this, and so we will label it like this: A1G, EG symmetry, T2G orbitals, so T1U are obtained from this. These are T2G non-bonding. This is EG star, that is antibonding. This is A1G star, and this is T1U star, that is antibonding. So here we will have the orbital that is this pi star. So ligand will provide, this is empty and these are filled. So these are, we will show here, this is filled. These are also filled. We are not giving any specific example. So up to this level all the orbitals are filled, and because of this the transitions are taking place from this T2G to this pi star and this EG star to this pi star. So these are charge transfer bands. These are charge transfer bands. So from this diagram we can identify how the electrons are moving. This charge is moving from one place to the other in the ligands. So we have seen the characteristics. So these charge transfer bands shows a spin allowed type, means spin is allowed. Means spin remains the same. Spin remains the same. Spin is not changed or inverted. We will see some examples in which the interligand transitions, charge transfer transitions are taking place and the absorption bands are observed. So we are having some examples. So if we take the example of, say, this PtCl4, PtCl4, or you can show here this PtCl4 like this, 2 minus, PtCl4 2 minus. So in this case, the charge transfer bands, that is ligand to metal, charge transfer is ligand to, charge transfer is ligand to metal through pi. So this is pi bonding. So Cl first gives electrons to Pt, so they give sigma bonding, and the excessive accumulation of charge on platinum is given back to Cl minus. So that is charge transfer bands. Now we can show these in the absorption spectrum, or where we can plot here the epsilon max, which is given in the form of per dm cube, per dm cube per mole per centimeter. Now we can get the absorption spectrum like this. So here you can have the absorption spectrum. So the mu bar values per centimeter are shown here. So we can get this absorption band like this. So this will show the absorption bands, two absorption bands which are having the frequency, first having frequency 36,000 per centimeter, and it will have molar absorption, molar absorptivity epsilon 12,000. So this is for this band. Now for this band we will have the frequency nu bar at 44,000 per centimeter and molar absorptivity is 30,000. The unit is per cubic decimeter, that is volume, per mole per centimeter. Here we can have these transitions which are taking place in this way. With respect to symmetry, the 1A1G to 1EU to EU2 to B1G, and another is 1A2U, that is from 1BU, B2U, B2U to 2B1G, and the 1EU, that is 1EU to 2B1G. So the values of these two transitions are like this. So these are appearing at 36,000 per centimeter, whereas this appears at 44,900 per centimeter. Here, this ligand to metal charge transfer spectrum of PTCl4 is shown here. It shows that the usually pi symmetry orbitals are involved within the ligand itself. The pi symmetry orbitals within the ligand itself are involved, and their energies are therefore similar to those of the corresponding transitions in the uncoordinated ligand. Means the ligand which is either coordinated or uncoordinated, means free. The energies of these transitions are similar. Another example, we find here two types of bands. This is much stronger band, and these are relatively weaker bands. So this is the example of we have seen as ligand to metal. Now we will see another absorption band. There we find metal to ligand charge transfer. Metal to ligand charge transfer. Here the absorption spectrum appears like. So this epsilon is there, nu bar is there per centimeter. Then we can have the absorption bands like this. Like this. There are bands. This is very small, relatively larger, and this is the very strong band. So we will have the values like this. The nu bar value here it is 32,300. 32,300. Epsilon value is 700. Then this will have the values this will have the values mu bar 35,200 and epsilon value is 4,200. Then this will have the value mu bar is equal to 37,600 and epsilon is 10,600. Now this will have the transitions. You can show here like this. This is for NiCN4 2 minus in aqueous solution. In aqueous solution. So here nickel has filled d orbitals, whereas this Cn minus has vacant pi star orbitals. Now we will have here the transitions like this. The symmetry of these d orbitals is like this: 2a1g, 2eg, 2eg orbital, 2a1g and 2b2g, and this will have these ligand group orbitals, that is pi star, where we can have 3 charge transfer transitions, metal to ligand transitions, and these transitions are shown here. You can show here these transitions. So first is with A1G symmetry, we can have one B1U, that is 2 B2G to 2 A2U. Then second is 1 A2U symmetry orbital to 2 A1G, and this is showing charge transfer to 2 A2U. Third is A1G to this 1 EU, that is from 2EG to 2 A2U to A2U. Now if we show these absorption bands for these transitions, so these are 32,300 per centimeter. This will have 35,200 per centimeter, and this will have 37,600 per centimeter. The symmetry forbidden transition is G to U, means change in the symmetry is shown here. Now this transition, it is low lying, So this is very weak transition, but these two transitions are strong, so they are strongly appearing or visible in the spectrum. Now the third point is metal to ligand transition. That is metal to metal transition, charge transfer transition. So in this case, the examples contain two metal ions of the same or different type. So out of the two metal ions, one is in lower oxidation state and another is in higher oxidation state. And there is one bridging group, bridging ligand. So this acts as the conductor. We will show this in the example. So if we take the example, that is NH3 5Ru, NH3 5Ru, then mu PZ, that is pyrazine, then Ru is Ru, NH3 5U. So this we have high plus charge, that is CREUTZ, Cruz ion, Cruz ion, TAUBE ion. And the structure of this complex is Ru. So this is the structure of this Cruz ion. Here this pyrazine is the bridging ligand, and these are the two metals which are having which are stored in the different oxidation states. So as is expected, so this each of them, that is, it has 2.5 oxidation state or is thermal charge. So it has thermal charge on each Ru is 2.5 plus 2.5. So when they are showing the charge transfer from this metal to this metal, so one metal is oxidized and one metal is reduced. or alternately this is reduced and this is oxidized. As a result of this, the one metal comes in the 2 plus state, another metal ion goes into 3 plus state. So the oxidation state is shown to be changing in this way. So this we can have another example of this Prussian blue also. But we will see this how it takes place. Each metal ion is having the structure like this, means same thermal charge is there. But after charge transfer, means this charge, say 0.5 charge, is moving from this metal ion through this pyrazine. So this is pyrazine. So to this metal ion. As a result of which this metal ion becomes 3 plus. So after charge transfer, this becomes 2 plus and this becomes 3 plus as a result of charge transfer. So this is a small or shorter bridge. The charge transfer is possible between the metals because this pyrazine is a short bridge. But instead of this short bridge, if there is a longer bridge, then the metal ions are separated to a greater extent. In that case, the charge separation is not, means charge transfer is not very easy. So under this, if instead of this pyrazine, if there is 4 prime, this dipyridine. So in that case, the greater distance between the centers are separated by longer distance. As a result of this, the delocalization of electrons is difficult. So in that case, one of the metal has higher oxidation state and another metal will come into lower oxidation state. The charge transfer is possible only if this bridging ligand is shorter. So with this we will stop our discussion, and we have completed this point of charge transfer, and next time we will discuss the next point and last point of this topic, that is this nepheloxiatic effect. So till then, see you next time. Please subscribe if not yet to this channel. Also press the like button and bell icon, and you can also put your comments. So this topic is specially prepared for MSc course. So the MSc students as well as the students which are appearing in the competitive examinations such as MPSc and UPSC may find that this topic is helpful to you.